second video on logistic regression. So in the first video we established a couple of things. One is how to evaluate the error of a probability prediction p hat. And the error function that we said makes sense is this expression. And we also learned how to go from the weight vector w, sort of the state of the learning machine, to a probability prediction. And the way that we plan to do that is to take the dot product of the weight vector and the instance vector and then run that through this function called the logit function that has a range that goes continuously from 0 to 1. Okay, so now the question is, how are we going to use the error that we discover to improve W? So we need kind of a smooth way to do that. So let's talk about how that could be possible. So I'm going to put these expressions together. So here we're saying that p hat is equal to this, and I have this piecewise defined function. So what happens if you actually substitute theta in where p hat is in this expression? Then you get minus natural log of theta of w dot product x if y is equal to plus 1. And you get minus natural log of 1 minus theta of w dot product x. Whoops. If y is equal to minus 1. Okay, so here's one reason that the logistic function is extremely nice. It just happens to have this property that 1 minus theta of s is equal to theta of minus s. So this is pretty easy to verify algebraically, but let's just do it together. So what is this? We can write this as 1 plus e to the minus s over 1 plus e to the minus s minus 1 over 1 plus e to the minus s. And what does that come out to? That comes out to the 1's cancel on top, and you get e to the minus s over 1 plus e to the minus s. Now if you multiply top and bottom times e to the s, you get 1 over 1 plus e to the s, which is exactly the logit function with minus s plugged in. All right, so that greatly simplifies this case-wise defined function. Let's do it in a few steps here. So we've just established that this is the same thing as, maybe it would be easier just to cut and paste. Okay, except that now in this bottom expression we can erase this 1. Let's just erase everything in there actually. And the thing that's in there is equal to theta of minus wtx. Okay. So now, many years in the past, some very intelligent person observed that the only difference between the upper branch and the lower branch now is that the upper branch is positive, the lower branch is negative here. But that also exactly reflects whether y is plus 1 or minus 1. So you can eliminate the cases and just write this as minus natural log of theta of y times wtx. Okay. All right. And we can go even further. Sorry, we're chasing this other stuff off the screen here. We can use the property of natural logs about shoving exponents in. So I'm going to take this exponent of negative 1 and push it inside. So this becomes natural log of the reciprocal of theta y wt x. And this is the same thing as natural log of 1 plus e to the minus y wt x. Okay, and why is that last statement true? It's because this is the expression for theta. So if you take the reciprocal, you just get 1 plus e to the minus input, and that's exactly what this is. So this is kind of interesting. Now I'm going to make a connection between logistic regression and the perceptron. Maybe before I do that, I should say what it is we do with this thing now. So what we have now is a nice simple expression for the pointwise error when w is the weight vector and the inputs being considered are w and y. So it turns out that this thing has a simple gradient. In fact, we can compute it right now. What is the gradient of e when w is the variable vector? Well, when you take the derivative of natural log of an expression, it's the derivative over the expression. So I just copy 1 plus e to the minus y wt x down here. And now you have to think for a second about what comes out. So obviously the derivative of 1 is 0. The derivative of e is itself, so that's this, wtx. And now finally we're just left with taking the gradient of y wtx, and we've been through this in class. You know, this is just a constant, and when you take the gradient of a vector times another vector, the result is just that. And okay, so we have, and of course the y is still there also. So this is, and there's a negative sign. So minus y x bar. Okay, and notice that this is a vector quantity. Okay, great. So now that we have the gradient of the pointwise error, if you want, you can simplify this. This is just minus y times x bar. You know, this is a scalar times a vector here, plus 1 over 1 plus e to the y wt x. Okay, so now using this formula, you can easily write a program that does stochastic gradient descent to optimize w. So of course, in stochastic gradient descent, the update rule is just the new weight vector is equal to the old weight vector minus the learning rate times the gradient of the pointwise error. And so if you do this repeatedly in various epochs and adjust the learning rate accordingly, then you should get good convergence. So that's how you train a logistic regression model. And if that's all you care about, you could stop watching now. But I want to show you something else that's kind of cool. Where are we here? I had to come back into my studio, so I think I'll just say hi. How you doing? Now let's go back to the web browser. And what I have here is the Wikipedia page for what's often called the ReLU function. So the ReLU function is just the maximum of 0 and the input. This is often used in training deep neural networks. That's the only reason that I was aware of it anyway. So this blue line here is the graph of the ReLU function. This green line is the graph of something called the soft plus function that approximates, it's a differentiable analog of the ReLU function. And if you go down and look at the expression for the ReLU function, the soft plus function, you can see it right here, and that should look pretty familiar, right? So let's just do, this should probably be a separate video, but I'm just going to do it here.